Hey guys, chapter 10, hypothesis test, this time for standard deviation. All right, so remember with standard deviation, we'll be using the chi-square distribution. That's what we were using when we were constructing our confidence intervals. And that's what we're going to use for our hypothesis testing about the standard deviation and for variance too, if we need it for that too. All right, so if a simple random sample of size n is obtained from a normal distribution population with mean, mu, standard deviation, sigma, then chi squared is equal to the degrees of freedom times our sample variance divided by our population or variance. And that has a chi-square distribution with n minus 1 degrees of freedom, where s squared sample variance. All right, characteristics of the chi-square distribution. 1, it's not symmetric. 2, the shape of the chi-square distribution depends on the degrees of freedom, just like the student C distribution. 3, the number of degrees of freedom increases, the chi-square distribution becomes more nearly symmetrical, or we could say more normal-ish. The values of chi-square are non-negative, so that's another thing. So we don't have an area to the left of 0 whatsoever. It starts at 0 and then makes its way to positive infinity. So starts at 0, makes its way to positive infinity. So this is what we're looking at here. Now, test hypothesis about the population standard deviation. And testing hypotheses about the population variance or standard deviation. So to test hypotheses about the population variance or standard deviation, we can use the following steps, provided that the sample is obtained using a simple random sample. Population is normally distributed. And again, we have our two-tailed test, left-tailed test, right-tailed test. Again, remember that two-tailed test, our alternative is not equal to. A left-tailed test, our alternative is less than. Right-tailed test, our alternative is greater than. And select a level of significance depending on the seriousness of making a type 1 error. Next, compute the test statistics. So test statistic, this is for our classical approach. We're comparing our test statistic to our critical values or critical regions. Critical values are chi-squared left, chi-squared right. If it's to the left of chi-squared left, it's in the critical region. If it's to the right of chi-squared right, it's in the critical region. And again, this is just the verbiage of this picture. If we fall in these shaded regions, then we would reject, which is just what they're saying here. And step 5, state the conclusion. All right, so here by hand, our p-value approach, compute the test statistic and not use a table. We're going to use Excel to see what our probability is of falling into these rejection regions. If the p-value is smaller than our significance level, then we reject. If it's not smaller than our significance level, then we do not reject. And that's what we have there. And same thing here. So the procedures in this section are not robust. Therefore, if analysis of the data indicates that the variable does not come from a population that is normally distributed, the procedures presented in this section are not valid. All right, next in the sample or in the example from section 10.3, quality control engineer for M&M Mars tested whether the mean weight for the fun size Snickers was 21 or 20.1 grams. Suppose that the standard deviation of the weight of candy was 0.75 grams before the machine recalibration. The engineer wants to know if the recalibration resulted in more consistent weights. Conduct the appropriate test at the alpha equaling 0.05 level of significance. All right, here's the data, but actually it looks like the exact same data that we have up here. All right, so what we'll do instead is just take a copy of this and take it to a new sheet. All right, but things are going to be just a little bit different, like alpha is equal to 0.05, and let's see. All right, so mean weight of the fun size Snickers was 20 grams. Suppose that the standard deviation of the weights of the candy was 0.7. So 0.7, this is before the recalibration. So here, what they're meaning to say is just that our standard deviation is equal to 0.75. The rest of the data we could actually get from here. Conduct the appropriate test at the alpha equaling 0.05 level significance. All right, coming over here, let's toss everything into Excel. So again, the very first thing we're stating is that the standard deviation is 0.75. And let's take a look at the rest of it. So we need S squared, or the sample variance, which is equal to sample variance is VAR of a population or a sample. It's going to be from the sample, this here. And we have our sample standard deviation. We also need to know what N is. N is equal to the count of these values here. 11, perfect. Our degrees of freedom equal to this value minus 1. Alpha is 0.05 level of significance. All right, and from here, let's just see what we're going to need. So we could start off with our classical approach. So classical approach, and over here will be our p-value approach. So classical approach, we are going to look at our, let's see. Actually, let's do our hypothesis testing before we start with that. So hypothesis test, we have our null hypothesis. And the null hypothesis is that the standard deviation is equal to 0.75. And the alternative is that our standard deviation, actually, let's see what they say. The engineer wants to know if the recalibration resulted in more consistent weights. So let's think about it. More consistent weights means less variability. So less variability means a smaller standard deviation. So what they're saying is that the standard deviation in this case would be smaller. So, so less than. Less than 0.75. All right. Oh. And now with that, we could check out the rest of it. All right, now we could look at our classical approach. So thinking of what is going on here, what we have is a left tail test. Remember left tail because our arrow here is pointing to the left. So we have this area here, and because alpha is equal to 0.05, this area is equal to 0.05. So classical approach is we're going to find our chi-squared value. So chi-squared value. And that's going to be the value right here. So this value right here. If our test statistic is smaller, then we would reject. Or if our test statistic falls into the critical region, then we would reject the null hypothesis and accept the alternative. Otherwise, we're not going to do anything. So here, what we're looking at is our critical value. So critical value, chi-squared value. So again, we're looking at whatever this value is. So we're given this area and also the degrees of freedom. So here, chi-squared value. So chi-squared distribution or chi-squared inverse. Do we need an area, or do we have an area? Do we need an area, or do we have an area? This time we have an area that we're looking for that chi-squared value for. And let's see, so probability here is going to be the area of 0.05. The area to the left of that value. Our degrees of freedom, have it conveniently here. And there we go. So that value is 3.94. Now that we have that, we could compare it to our test statistic. And for the test statistic, the chi-squared value for this, remember that chi-squared is equal to our degrees of freedom times our sample variance divided by our population variance. And there we go. So this is equal to our degrees of freedom, our numerator. So degrees of freedom times our sample variance. And we're dividing this by our sample standard deviation. So this one, we only have our population variance. This time we have standard deviation, so we're going to have to square it. So parentheses for the bottom, this value squared. And there we go. So 7.29. 7.29 is actually greater than 3.49. So we are not in that rejection region. So not in the rejection region. So our test statistic is not in the rejection region. So we will not reject the null hypothesis. We do not have sufficient evidence at the 5% level of significance to reject the null hypothesis. All right, so that's our classical approach. We don't have sufficient evidence to reject anything. So we can't make that conclusion. All right, so we have that. Next, let's look at our p-value approach. Let's see what that probability of falling into that category is. So this time we're less than. So what we're going to look for is the probability of our standard deviation, or actually our sample, being less than, what was our standard deviation? Our sample standard deviation being less than 0.75. And because Excel is already going to look at the data to the left or whatever value we give it, we don't have to do anything too crazy here. So here we just have to test that probability. So equal to a chi-squared distribution. So chi-squared distribution or chi-squared inverse. Do we need an area or do we have an area? Because we're looking at that probability, we're looking for the probability, we're going to use chi-squared distribution. Here, X in this case is going to be our test statistic because they already did all the work for us, comma, our degrees of freedom, comma, cumulative. Do we want just that value, the area under just that value, or do we want that entire accumulated area? For these, we want the entire accumulated area, everything smaller than. All right, so 0.30. So this is the probability of S being less than 0.75. So because we don't have a tiny value, we don't have, what we were looking for here is for the value to be very, very unusual, or for any unusual values. 30% is not unusual. If you have 30% chances on things, those values are not unusual. So since our p-value is greater than our significance level, we do not have sufficient evidence, or we could actually put the values here. So 0.302 is greater than 0.05. We do not have sufficient evidence to reject the null hypothesis. And because we came to that same conclusion, we could just copy and paste this. And there we go. That concludes this problem. So we don't have enough evidence to reject anything. All right, let's see if we forgot anything. So normal probability plots show refers at the for the reference example, a plot indicates that the weights of candy could come from a normal or a population that is normally distributed. So we need evidence. Step one, we need evidence to conclude that the population standard deviation is less than 0.75 grams. So this can be written just like this, left tail test, cool. And they gave us level of significance being 0.05. Classical approach, we find our test statistic and compare it to our critical value. And here it did not fall within our critical region, it fell outside of the critical region. So we do not have sufficient evidence to reject the null hypothesis, which is what we stated there. And now looking at the p-value approach, again, that same chi-squared value, that same test statistic, we're going to look at the probability of it being less than our actual mean. And we found that with 10 degrees of freedom, that value was, where was that value? So it's greater than 4.865. There we go. Sample standard deviation. What value did we get? So 30%. So there was a 30% chance that we would be less than that value there, less than the standard deviation, which is what they got right here. So the p-value ended up being 0.30, which the p-value was a lot greater than the significance level or level of significance. So we would conclude that there is no sufficient evidence at the alpha equaling 0.05 level of significance to conclude the standard deviation of the weight of the fun size Snickers is less than 0.75 grams. So it appears that the recalibration did not result in more consistent weights. So that ends 10.4. If you guys have any questions, so this is all the homework that you guys are going to have for this chapter. If you guys have any questions, go ahead and email me. If not, good luck. Bye.